Okay. Unit number 2 is mobile radio propagation. Mobile radio propagation. The mobile radio propagation is nothing but the different propagation effects are there. One is propagation of light, propagation of sound, and propagation of wave. Okay. In this unit, the most important points are nothing but what? Two derivations will come in this. The two derivations will come. Those two derivations are very, very important. But yesterday it has declared that the exam is of online. If it is offline, they will ask you the fixed question for 8 marks, one derivation for 6 marks, and one derivation for 8 marks. But for the knowledge point of view, you have to give concentration for this mobile radio propagation. And which are the syllabus contents for this mobile radio propagation is large scale path loss, free space propagation model. Large scale path loss and free space propagation model both are same. Both are same. Large scale path loss. Large scale is nothing but for a longer distance. Path is nothing but a distance. For a longer distance, what are the gains and which are the losses present in that particular signal. Same for free space propagation model. Free space is nothing but that has to be this can also use for a longer distance communication. Both the words or both the sentences are same. So there is one derivation based on this large scale path loss and free space propagation model. In this large scale path loss and free space propagation model, we are going to calculate a total received power at the receiver end, at the output. We have to calculate the total received power, that is P of R. P with respect to R. PR of that is equals to the sum of the parameters are present. Some of the parameters are present for calculating this free space propagation model. Those parameters are how much is the transmission power, how much is the transmission gain, how much is the transmission gain, how much is the received gain, and how much is the distance between the transmitter and receiver, and what is the wavelength, and what is the frequency band. That has to be calculated by this free space propagation model. We'll see the derivation once it starts. And in second, we have to calculate, we have to see the derivation of ground reflection model. Ground reflection model. In bracket he has written two-ray model. Ground reflection model or a two-ray model, again there is a big derivation comes, that is two-ray model. There are two rays are present in this ground reflection model. One is a direct line of sight model. The first wave, the first ray is direct line of sight, or second ray is ground reflection ray. One is direct line of sight wave, second is ground reflection wave. These are the two waves present in this ground reflection model. This is a big derivation, we'll see. And diffraction. Diffraction is nothing but whatever the signal we're transferring, that signal will going to effect for a physical things, physical objects. Physical objects are nothing but when the signal is transferring through air, there are some of the physical objects present, the number of buildings are present, number of trees are present, number of vehicles are roaming in between. So that signal has to be going to reflect back and it should be diffracted towards the edge of a particular devices, that is a diffraction. And next, practical link budget using path loss model. Practical link budget using path loss model. In this, we are using the mainly two links. One is in uplink, one is downlink. One is uplink, one is downlink. Or you can call other name for uplink is that is of forward link and reverse link. Forward link and reverse link. These are the two links present in a practical link budget for calculating how many gains are present and how many losses are present in a particular system. How much is the gain and how much is the loss present in a particular system, that has to be calculated in practical link budget using path loss model. Next, small scale fading and multipath small scale multipath propagation. The fading is nothing but the signal is not visible properly. You are watching television, so due to some signal, due to bad signal, the picture is not that much clear. The picture of the image of that picture is not that much clear. So that is going to fade due to some disturbances, due to some collision between the two signals. That is what fading. Small scale fading. This fading is going to effects for different multipaths, different multi-propagations, different multi-propagation. This is a very small unit. Unit number 2 and unit number 3 is very small units. Only 4 points are present in unit number 2, and in unit number 3 again the 4 points are present. That is large scale path loss model, free space propagation, ground reflection model or a two-ray model, diffraction, practical link budget, small scale fading, and multipath. Two derivations are very important in this unit. We'll start with the point number 1, large scale path loss or free space propagation model. I already told you the free space propagation model is nothing but the signal can be propagated for a longer distance from Earth to the satellite. We are sending the information from Earth to the satellite, that is for a free space. How they are going to calculate when you are sending the information from Earth to the satellite? They are going to see how much is the transmitter's power, how much is the transmission gain, how much is the received gain, how much is the wavelength, and how much is the distance, and what are the losses present in that particular signal. All these parameters they are going to consider. He has written here free space propagation model. The free space propagation model is used to predict the received signal strength. Whatever signal you are sending, whatever the signal you are getting at the Earth station, how much is the strength of that signal, how much is the performance, how much is the efficiency of that signal, that has to be calculated this free space propagation model. When the transmitter and receiver has a clear line of sight between them. When the transmitter and receiver is having a clear line of sight between them, so we'll get a better quality of service. We'll get a better signal at the receiver end. Two parameters, one is satellite communication. For example, satellite communication and microwave line of radio link. These are two parameters we are using for this free space propagation model. We are sending any of the signal from Earth station to the satellite. So that satellite should be a clear line of sight between the satellite to the Earth station. Then only you'll get a clear picture in your television. Okay. For this, they are using the one formula or one equation for calculating this free space propagation model. That is, the formula is FRIS, F-R-I-I-S. Free space equation. Free space equation, that is depending on the received power with respect to the distance between the transmitter and receiver. That is PR of D, in bracket PR of D is equals to PT, GT, GR lambda square whole divided by 4 pi whole square D square into L. Write down this formula. Based on this, we are going to calculate the numericals. I am telling you to write this equation. Only the equation you have to write. Everyone, once I started calculating the numericals, you have to show me the answers by showing the video. Okay, everyone has to solve the numericals. The PR of D is equals to what? PT, GT, GR lambda square divided by 4 pi square D square into L. The individual parameter explanation is PT stands for transmitted power, transmitted power. The PR of D is a received power. G of T is transmitter antenna gain. G of R is receiver antenna gain. And D is the distance between the transmitter and receiver. L is the system loss, and lambda is the wavelength in meters. How to calculate lambda? Anyone knows the formula? Calculation of lambda, that is wavelength. Lambda is equals to what? Lambda is equals to
C by
what?
F.
Very nice. Lambda is equals to what? C by F. The C is nothing but the speed of light, velocity of light. That is a 3 into 10 raised to 8. The value is constant for C, that is 3 into 10 raised to 8. He has given a frequency. Based on that frequency, you have to calculate the value of lambda. I think you have written this formula, that is PR of D is equals to PT, GT, GR, lambda square divided by 4 pi square D square into L. You have to know this points, that is PT is transmitter power, GT is transmitter gain, GR is receiver gain, lambda is wavelength in meters, D is the distance between the transmitter and receiver, L is nothing but the system loss, and PR of D is received power with respect to the distance of transmitter and receiver. Based on this equation, there is a system loss is present, that is L. System loss is present, there is L. So L is greater than 1. If a loss in the system is greater than 1, indicates loss due to transmission line attenuation, filter losses, and antenna losses. Due to some disturbance in the signal or the antenna is not working properly, this loss is going to happen. If L is equals to 1 or less than 1, there is no loss in the system. There is no loss present in a particular system. So you have to remember this. L, always, if he has not given the value of L, if he has not given the value of L, you have to mention the value of L is 1. Write down. If he has not given the value of N for a numerical, for examples, L must be 1. There is no loss in the particular system. Depending on this free space equation, we have to calculate the gain of antenna. The gain of antenna between the transmitter antenna and the receiver antenna. The total gain of antenna can be calculated between the transmitter antenna and the receiver antenna. Okay, that comes in next. The gain of antenna is related to the effective aperture. The gain of antenna is related to the effective aperture that is assigned by A with respect to E. A oblique E. Effective aperture. Write down this, all the equations are. Based on that, there are number of numericals will come. The gain of antenna is related to its effective aperture, that is AE, is given by the G is equals to 4 pi AE divided by lambda square. 4 pi AE divided by lambda square. I think you are writing the formulas. The gain of antenna with respect to effective aperture, that is A oblique E, is given by G is equals to 4 pi AE divided by lambda square. With this effective aperture is related to the physical size of antenna, means your base station, means that is your tower. That tower is called as your effective aperture. Based on that, you have to calculate the wavelength of that particular antenna size. Particular antenna, the wavelength has to be calculated, that is lambda. Lambda is equals to what? C divided by F. Lambda is equals to what? C divided by F. What is C stands for? C stands for a speed of light. C stands for a speed of light. The value for C is, write down, the value for C is 3 into 10 raised to 8. 3 into 10 raised to 8. 3 into 10 raised to 8. and PT and PR must be same units, and GT and GR are dimensionless. There is no dimension for GT and GR. Based on this effective aperture, you have to calculate the effective isotropic radiated power, EIRP. EIRP can be calculated at the transmitter side itself. Not it should be it is not going to calculate at the receiver side. Effective isotropic radiated power in short form, that is called as EIRP. Write down. In MCQ, they will ask you for a question for 2 marks or for 1 mark for a numerical. Calculate EIRP, that is using this formula you have to calculate the EIRP. If you have written these formulas, easily you can calculate the numericals in MCQ type of questions. If you know the formulas directly, that is PR of D is equals to PT GT GR lambda square divided by 4 pi square D square into L. If he has not mentioned L, you have to take L as 1. If you want to calculate the G, that is to be G is 4 pi A divided by lambda square. Next, lambda, if you want to calculate lambda, here he has mentioned the frequency of that particular system. So lambda is equals to what? C divided by F. Similarly, for effective isotropic radiated power, that can be calculated at the transmitter side itself. So EIRP is equals to PT into GT. EIRP is equals to PT into GT. So that has to be calculated in transmitter side itself. So for a free space propagation, you have to calculate the path loss. You have to calculate the path loss. Path is nothing but a distance. Path is nothing but what? A distance. The path loss PL represents the signal attenuation and is defined as a difference between the effective transmitted power and the receiver power. The path loss, that has to be given in decibel value. That has to be given in, substituted in decibel value. So path loss PL of dB. Write down these equations. PL of dB equals to 10 log of PT divided by PR. Here he has written a direct equation, that is minus 10 log of GT/GR lambda square divided by 4 pi square into D square. How this equation has come? The formula for path loss, that is PL of dB is equals to what? 10 log of PT divided by PR. 10 log of PT divided by PR. What is the equation of PR? This PR equation you have to substitute. Here PR equation. That is 10 log of PT divided by PR equation is what? PT GT GR lambda square divided by 4 pi square D square into L. If you want to divide, if you want to substitute that PR equation here, so you will get that equation. He has substituted. PT BT get cancels. Remaining is 10 log of GT GR lambda square divided by 4 pi square D square into L. L is 1. So he has mentioned here minus of 10. That he has directly substitute, that is GT/GR minus of this. So he has given directly minus substitution, that is minus of 10 log of GT/GR lambda square divided by 4 pi square into D square. Write down this equation for a path loss PL of dB. PL of dB is equals to the formula for this path loss. PL of dB is equals to what? Minus of 10 log GT/GR lambda square divided by 4 pi square into D square. If the gain of antenna is unity, so G is equals to what? GT into GR. G is equals to what? GT into GR. The gain of antenna is unity, that is becomes 1. So GT/GR will become 1. If he has mentioned the gain of antenna is unity, So GT/GR will become 1. So the modified equation, for this path loss, that becomes minus 10 log of lambda square divided by 4 pi square into d square. Why? Because they are issued a unity gain. The gain of antenna for respective antenna for GT and GR is unity. So GT/GR will becomes 1. Without antenna gains, with the unity antenna gains, the path loss is PL is equals to minus of 10 log of lambda square divided by 4 pi square into d square. So that has to be given in this. Write down this. PL is equals to minus 10 log of lambda square divided by 4 pi square d square. This formula is applicable when the gain of antenna is unity. This formula is applicable when the gain of antenna is unity. The above formula is applicable when he has given the transmitter gain and the receiver gain. In the equation or in the examples he has given, if he has given the transmitter gain and receiver gain, you can use that formula. If he has not mentioned, if he has mentioned the gain of antenna is unity, you can use this path loss equation, that is PL is equals to minus 10 log of lambda square divided by 4 pi square into d square. Similarly, for this, if you want to calculate for a longer distance communication, there is a one word that is called as a Fraunhofer region. That is a Fraunhofer region that has to be calculated with respect to the distance between the transmitter and the receiver. The Fraunhofer region can be given by d with respect to f, that is d oblique f is equals to 2d square divided by lambda, capital D, not a small d. Write this equation. Many numericals will becomes under this Fraunhofer region. The d oblique f is equals to 2d square divided by lambda. 2d square divided by lambda. So capital D stands is the largest physical linear. D is the largest physical linear dimension of the transmitter antenna. That is to be the distance between the transmitter and receiver, that has to be calculated for a physical linear dimension. So that has the d of f is equals to 2d square divided by lambda. You write this equation. And for calculating this, the total received power, okay, that has to be given by PR of D is equals to PR of D naught divided by D naught, PR of D naught into D naught divided by D whole square. PR of D naught into D naught divided by D whole square, that has to be given by the received power in a free space. Just 2 minutes, sir. The total received power can be calculated with respect to distance d is called as, that is PR of D naught initial distance, that is D naught is initial distance from the transmitter and the D is from initial to the final from a transmitter and receiver with respect to the square, that is to be given in this received power. The PR of D is equals to PR of D naught into D naught divided by D whole square. This received power can be represented in a milliwatt and a watt. In two representation can be done in these two methods. If you want to write it in milliwatt, the formula can be given by PR of D is equals to 10 log of PR of D is equals to 10 log of PR of D naught divided by 1 milliwatt he has given. That is, milli is nothing but what, 10 raised to minus 3. That becomes 0.001 watt. 0.001 watt. You have to modify that equation, above equation, into the decibel value. The decibel equation. Square will become 10 into 2, that becomes 20. Instead of 10 log, there is a square. So 10 into 2, that becomes 20 log of d naught divided by d. The equation will become like this. That is, of PR of d is equals to 10 log of PR of d naught divided by 0.001 watt plus 20 log of d naught divided by d. Write down this equation. This is also very, very important. PR of d is equals to 10 log of PR of d naught divided by 0.001 watt plus 20 log of d naught divided by d. If he has given for 1 milliwatt, but if you want to represent this PR, that is total power, in watt instead of milliwatt, what is the equation? PR of d is equals to 10 log of PR of d naught divided by 1 watt. Instead of 0.001, write down divided by 1 watt plus 20 log of d naught divided by d. Write this one more equation. PR with reference to 1 watt is represented as PR with reference to 1 watt is represented as, the equation is, I am telling you, write down this. PR of D equals to 10 log of, in bracket, PR of D naught divided by 1 watt 1 W plus 20 log of D naught divided by D. This is for another equation for 1 watt. This is another equation for 1 watt. So you have calculated the total received power for free space propagation models. There are number of equations will be coming in this for calculating this total received power. 2 minutes. Okay, I think you have written this equation. The first equation for this free space propagation model is the total received power. If those who are not written, write this equation. PR of D is equals to PT GT GR lambda square divided by 4 pi square D square into L. This is the first equation. Okay. Second equation for this is, if there is no loss, L is equals to 1. If there is a losses, the L is greater than 1. For calculating gain of antenna with respect to effective aperture, G is equals to 4 pi AE divided by lambda square. G is equals to 4 pi AE divided by lambda square. Second equation, that is, this one is third equation, that is for calculating wavelength, lambda is equals to C divided by F. Lambda is equals to C divided by F. And for calculating effective isotropic radiated power, that is EIRP, is equals to PT into GT. EIRP is equals to PT into GT. And for calculating a path loss, path is nothing but the distance. If the distance is more, there are a number of losses has to be present. So path loss equation for this is minus 10 log of GT GR lambda square divided by 4 pi square into D square. If the gain of antenna is unity, GT GR will becomes 1. So modified equation for this path loss is minus 10 log of lambda square divided by 4 pi square into D square. And next equation for calculating the Fraunhofer region, if the distance is more, D oblique F is equals to 2D square divided by lambda. Fraunhofer region, that is D of F is equals to 2D square divided by lambda. And lastly, for calculating this PR of D with respect to initial and with respect to maximum distances, that is to be given by PR of D is equals to PR of D naught. D naught is nothing but the initial distance, starting distance. PR of D naught into D naught divided by D whole square. This can be represented in two terms, PR, that is to be in 1 milliwatt or in a 1 watt. The 1 milliwatt equation is PR of D is equals to 10 log of PR of D naught divided by 0.001 watt plus 20 log of D naught divided by D. If it is for a 1 watt, PR of D is equals to 10 log of PR of D naught divided by 1 watt plus 20 log of D naught divided by D. These are the sum of the equations you have to write down, and this one is one of the example I will tell you, and next I will give you the example, you have to solve it. If a transmitter produces 50 watt of power, express the transmit power in units, that is in decibel milli and decimal watt. Means what? You have to calculate this decibel milli, decibel watt. These are the two equations, last equation I have given. If 50 watts is applied to a unity gain is given. Unity gain is nothing but what? GTGR will become 1. GTGR will become 1 with a 900 megahertz of carrier frequency. Frequency is given, so we can calculate a lambda. Find the received power in decimal milli at a free space distance of 100 meter. Your distance he has given, that is D has given, that is 100 meter from the antenna. The PR of 10 kilometer, that is already has given 10. Assume unity gain for a receiver antenna. This is what the solution for that example. He has given a transmitter power, that is 50 watt. See this? If a transmitter produces 50 watts of power, transmitter equation में असाइन किया है, that is PT. Transmitter produces 50 watt of power. If transmitter produces 50 watt of power, that is PT. PT will become 50 watt. Carrier frequency how much? That is 900 megahertz. Transmitter power PT 50 watt. Carrier frequency FC is equals to 900 megahertz. What do you have to calculate? You have to calculate the transmitter power in decimal milli and decimal watt. Before that, you have to calculate the total power, that is PR. First, don't see A and B. See third, the received power can be determined. I have already told you the formula for that. PR is equals to PT GT GR lambda square divided by 4 pi square D square into L. What is mentioned in the example? He has mentioned a unity gain. That is GTGR will become 1. Transmitter power is 50. You have to calculate lambda. For calculating lambda, that is C by F. Frequency is how much? 900. C is how much? 3 into 10 raised to 8 divided by 9 into 10 raised to mega is 10 raised to 6. So that value is 1 by 3. 1 by 3 whole square. Whole divided by 4 pi square. D is how much? Distance how much he has given? 100 meters. So he has mentioned 100 square. L. He has not mentioned any L. So loss of that particular system is 1. There is no losses. So the final answer for this received power. This type of questions will arise in your MCQ. So that is a PR is equals to what? 3.5 into 10 raised to minus 6 watt or 3.5 into 10 raised to minus of 3 milliwatt. If you want to convert that particular value into decibel value, in decibel form, so PR of decibel milli, if you want to convert the particular value into decibel, just you have to apply 10 log of that resultant value, 10 log of PR of milliwatt, 10 log of how much you are getting? 3.5 into 10 raised to minus 3 milliwatt, 10 log of 3.5 into 10 raised to minus 3 milliwatt. So that for this decibel value is minus 24.5 dB meter. Next, you go for A. Next, see the A. Transmitter power in milli. So 10 log of PR of milliwatt divided by 1 watt. So 10 log of, he has given already PT value. Milli is there, that becomes 10 raised to minus of 3. 10 log of 50 into 10 raised to minus 3, that becomes 47 decibel per milli. Getting? Transmitter power with respect to watt. I have given the second equation. Second equation, that is 10 log of Pt into watt. 1 watt is Pt into watt divided by 1 watt, that is 10 log of 50. It becomes 17 dB watt. 17 dB watt. So we have calculated all the parameters what he has asked in the example. You have calculated the total received power, that is PR. You have calculated the transmitter power with respect to milli and the transmitter power with respect to watt. And final, he has mentioned in the question that what is PR of 10 kilometer, total received power of 10 kilometer. That is what the received power at a 10 kilometer can be expressed in terms of decimal milli using equation, that is 3.9, where D naught initial D naught initial, this 100 meters, that has to be considered as initial distance. That has to be considered as initial distance. So D naught is equals to 100 meter and D already has mentioned 10 kilometer, that is final distance. 100 meter and D is equals to 10 kilometer. What is the formula? Here it is, formula. Okay, they are converted in decibel watt. PR of D is equals to PR of D naught into D naught divided by D whole square. If you convert that equation in decibel value, PR of D is equals to 10 log of PR of D naught plus 20 log of D naught divided by D naught divided by D. So final equation for calculating this PR of with respect to 10 kilometer is PR of D naught is what? 100 plus 20 log of 100 divided by 1000. You have already calculated PR of 100. PR of 100 is nothing but initial distance. For 100 meter, you have calculated the PR. That is what? Minus 24.5. Minus 24.5. That is already there. You have to calculate for 10 kilometer. Just you have to apply this 20 log of 100 divided by 100. That value is minus of 40. Minus 24.5 decibel milli minus of 40. The final answer for this PR of 10 kilometer is minus 64.5 decibel milli. Minus 64.5 decibel milli. So this is how we are going to calculate examples based on Freespace equation. I hope you all have written all the equations, and I shown you one of the example here, and based on this example, some of the examples will solve in the next lecture, that is of tomorrow's lecture. Tomorrow's lecture will solve 3 to 4 numericals examples so that you came to know how to solve the particular examples for this space propagation model. Okay, got it?
Yes, sir.
On Wednesday, I am going to take unit test 1 on unit number 1. Unit test 1 on unit number 1. Be prepared for unit test 1 on Wednesday. And on Friday, I will take your presentation. Friday, I will take your presentation. That is for a seminar. Wednesday, I will take unit test 1. Okay. And tomorrow we'll solve some of the
Okay, sir.
tests based on this space propagation model. Okay. Your attendance.